So we have seen so far that if you have a differential equation of the form mxy dx plus n of xy dy equal to 0. So if you have a differential, this is the first order differential equation. If you have a differential equation in this form, then we have seen that the condition that that this differential equation is an exact differential is that dou m by dou y equal to dou n by dou x. And if this condition is satisfied, then what you have here is an exact differential, and it can be solved very easily, and we have seen how to solve it. Now the question is, suppose you have a differential equation that is not exact. Okay, suppose this is not satisfied. Okay, so if this is true, then du equal to m dx plus n dy. Okay, you can write in that form. I've omitted the dependence on x and y. Okay, so it's understood that m is a function of x and y, and as is n. Okay, then du is an exact differential, and the solution can be written as u equal to du equal to 0 or u equal to constant. Okay, and we saw in the last class how you can solve for u. Now what happens? Suppose this is not an exact differential. So n of xy dy is not exact. That is, dou m by dou y is not equal to dou n by dou x. Okay. So if you have this situation, then it's possible to show that there exists a variety of integrating factors alpha, which is in general a function of xy. Okay. So there exists a large number of integration factors, or there exists one or more integration factors such that alpha m dx plus alpha n dy is exact. Okay. So there exist these integration factors such that alpha m dx and plus alpha n dy. So I am just multiplying this original differential equation by alpha, so I have the same differential equation. Okay, but then you have dou by dou y of alpha m is equal to dou by dou x of alpha n. Okay, where alpha is a function of x and y. Okay, so alpha is a function of x and y. So there exist these integration factors, okay, such that this is exact. Now the question is, how, if this exists, how do you go about finding the alpha? Okay, so in general, it is not easy to find alpha, because alpha will satisfy a differential equation. Okay, so we assume, or rather we look for integration factors that depend on a single variable. Okay, for example, alpha of x. So, so we specifically look for such integrating factors, not all, and you may or may not find it, but suppose alpha x is an integrating factor. Suppose alpha x, this is independent of y. So, suppose alpha x is an integrating factor. Okay. Then dou by dou y of alpha m is equal to dou by dou x of alpha n. Okay. Now, alpha depends only on x. Okay. So, this can be written as alpha dou m by dou y is equal to, and in this case you will have both terms. So, in this case, since we are differentiating with respect to y, alpha is independent of y, it comes outside the differential. So, you have alpha times dou m by dou y, and now in this case partial derivative with respect to x of alpha n will have two terms. First one will involve derivative with respect to x of alpha, and the second one will involve derivative with respect to x of n. So, the first term will be d alpha by dx into n plus alpha dou n by dou x. Notice this is a ordinary differential because alpha depends only on x, whereas this is a partial derivative because n depends on both x and y. Okay. And now I can rearrange this equation to write it as alpha dou m by dou y minus dou n by dou x. Okay, so I bring this here on this side is equal to n d alpha by dx. Okay, and this implies alpha d alpha by alpha is equal to 1 over n dou x into dx. Let me write it slightly differently. I will write it as 1 over alpha d alpha by dx is equal to this. Okay. Now, the left hand side depends only on x. So, the left hand side is only a function of x independent of y. I.e. independent of y. Okay. So, since alpha is only a function of x, d alpha by dx will only be a function of x, and 1 over alpha d alpha by dx will only be a function of x. So, the condition for alpha to be an integration factor is that the right hand side should also be independent of y. So, the right hand side has to be independent of y, and so the condition is that has to be independent of y. Okay. So, the condition for there to exist an integration factor alpha which depends only on x is that 1 over n dou m by dou y minus dou n by dou x has to be independent of y. Okay. So, if this condition is satisfied, if this is only a function of x, then you can calculate the integration factor by integrating out. So, the condition for there to exist an integration factor alpha which is only a function of x is that 1 over alpha d alpha by dx or has to equal this right hand side, or in other words 1 over n dm by dy minus dn by dx has to be a function only of x. Okay. Now, if this is a function of x, then we can integrate it out. So, you can say d alpha by alpha is equal to dou y x dx, and you can integrate this out. So, you will say natural log of alpha is equal to integral plus a constant. Okay. So, you just integrate both sides and you have a constant of integration. So, this is the constant of integration. Okay. So, the strategy is you calculate this quantity and you see if it is a function of x. If it is a function of x, then you are done, you have your integration factor. Okay. Now, another way to do this, instead of looking for an integration factor that depends only on x, we look for an integration factor. So, alternatively, look for integrated factor beta, which is only a function of y. So, beta is only a function of y, okay. It is independent of x, and you can go through the same arguments. So, you will say that you will say that instead of alpha you will have beta, okay, and you have the same condition, but beta depends only on y. So, in this case it will come outside the integral, and you can show that your condition will look like dy into m plus dou m by dou y is equal to beta dou n by dou x. Okay. And if you rearrange this, you will get something like 1 over beta d beta by dy is equal to 1 over m minus 1 over m dou m dou y minus dou n by dou x. Okay. And now, the left hand side depends only on y. Okay. So, the condition is that the right hand side should depend only on y. So, this has to be independent of x. So, if this is independent of x, if this right hand side is independent of x, then you can find this integration factor beta of y, and you can calculate beta in the same way by integrating out. Okay. So, what we notice is that in both these conditions, you have the same expression dou m by dou y minus dou n by dou x. In one case, you divide it by n and you should get a function that is independent of y. In the other case, you divide it by m to get a function that is independent of x. Okay. So, the usual strategy when we solve these differential equations is to first calculate this quantity, okay, see if you divide it by m or n, do you get the appropriate function that is independent of one variable. Okay. And if you get that, then you know that an integration factor exists. Okay. So, let us look at an example of applying this integration factor. So, let us take a specific example of a problem and see how we can calculate the integration factor. Okay. So, the problem is plus x square dy equal to 0. Now, the first thing you will say is that this can be solved by separation of variables, but let us go ahead and try to try to use the integration factor. Okay, so what we will do is dou m by dou y is d by dy of this is equal to 2x x. So you say that for x. Okay. Now, if I divide this by, so if I now look at 1 over n is equal to minus 4x by 3 x square, okay, is equal to minus 4 by 3 x, and it is independent of y. So, 1 over n dou n by dou y minus dou n by dou x is independent of y. So, alpha x exists. Okay, so you have an integration factor that depends only on alpha, and you can calculate this integration factor. So, you will say that ln alpha is equal to integral minus 4 by 3 x dx plus constant, okay, is equal to plus constant, and if you work this out, you will get ln of x to the minus 4 by 3 plus constant, okay, and you can write alpha is equal to e raised to c into 4 by 3. Okay. And this is just another constant, e raised to c is just another constant. So, alpha is equal to x to the power minus 4 by 3. Okay. So, the constant of integration, okay, we do not need to worry about this. So, we just choose this as your integrating factor. Now, if you choose this as an integration factor, then your differential equation becomes 2y. Now, if you multiply this by x to the minus 4 by 3, you will get x to the minus 1 by 3 dx plus 3. Now, you have x to the 2 by 3 dy equal to 0. So, I just multiplied this differential equation by x to the minus 4 by 3, and when you do this, then you can calculate, you can verify that one by 3 is equal to dou n by dou x, and dou n by dou x, if you, so you have 3 into 2 by 3. So, that is 3 into 2 by 3 x to the minus 1 by 3 equal to 2 x to the minus 1 by 3. So, clearly 2 x to the minus 1 by 3 is equal to dou m by dou y, and it is equal to dou n by dou x. So, this is an exact differential. And once you know that this is an exact differential, you can find your u by the methods that we discussed earlier. Okay. So, this is a procedure for finding the integration factor. First, you calculate dou m by dou y minus dou n by dou x. Okay. Okay. Then you look at your m and n, and you see whether dividing by n you get a function only of x, or dividing by m you get a function only of y. In this case, actually we could have also found an integration factor that depends only on y, because if you divide this by m, okay, then you will get a function only of y. Okay. So you can do it either way, and you should get the same answer. Now we can look at a general linear first order differential equation, and this is of the form dy by dx plus a of x into y equal to b of x. Okay. So it's linear because each term contains either y or its derivative up to first power. Okay, and this is inhomogeneous. So this is if b of x is not equal to 0, then it is inhomogeneous. Linear ODE. Okay. Now the question is, how will we solve this? So in order to solve this, we can use the method of integration factors, integrating factors, and you can go through the details and work out the solutions. Okay. In order to write the solution, we will first look at the homogeneous equation. So homogeneous the homogeneous equation dy by dx plus a of x y equal to 0. So this homogeneous equation can be solved by separation of variables. You take so this so if I take this on the right, then bring the y below. So this is just integral minus a of x dx plus constant. Okay, so this is the solution of the homogeneous equation, and I will call this yh. Okay, so the solution of the homogeneous equation is given by this. Okay. Oh, sorry, it should be e to the minus. So ln of y is equal to this. Okay. Now let me call this quantity w of x. Then this is minus plus some constant. In other words, the homogeneous equation has a solution. So e to the minus w of x times e to the c, and on that e to the c I will just write it as a constant, capital C. Okay, so this is the solution of the homogeneous differential equation. Okay, so the homogeneous equation means you put b of x equal to 0. Okay, now the inhomogeneous equation, the solution of this differential equation is related to the solution of this homogeneous equation in this form. So is equal to h of x times integral dx plus constant. Okay. So you can show by the method of integration factors. Okay, you look for an integration factor that depends only on x, and you can show that the integration factor will give you this final solution, and so finally you will get e to the minus w of x plus okay. So this is the general solution of the of an inhomogeneous linear first order differential equation. Okay. And I leave it as an exercise to you to verify that this is indeed the solution, and as I said, you can do this by method of integration factors. Okay, so that concludes the part of involving first order differential equations. I'll just summarize the strategy. So ODEs. Okay, so the strategy to solve first order differential equations is, first thing is to try to separate variables. Okay, so try to separate variables. If you are able to separate variables, then you separate it and you solve the differential equation. If you are not able to separate, then the next strategy is to check if ODE is exact. Okay. So you check if your ordinary differential equation is an exact differential. In other words, check if dou n by dou x. Okay, so if this is satisfied, then you can find the solution as u is equal to du equal to m dx plus n dy. Okay, so you can write du equal to m dx plus n dy, and solution is u equal to constant. So once you know that your ordinary differential is exact, then you can solve this. Okay. And the third strategy, if it is not exact, if by dou y not equal to dou x, okay, then the strategy is calculate one over n and so you calculate both these terms, 1 over m to 1 over n times dou m by dou y minus dou n by dou x, and 1 over m times dou m by dou y minus dou n by dou x. Okay. Then you check if this is only a function of x, or you check if this is only a function of y. If this is only a function of x, then you can find the integration factors. If this is only a function of y, you can find the integration factors, and then look for integrating factors. Look for integrating factors. Okay. So that is this is the general strategy for solving first order differential equations, and in case you are not, in case this is not independent of y and this is not independent of x, then there exists no integration factors, and you cannot solve the differential equation using these procedures. Okay. So now we'll start discussing second order differential equations, and how you solve second order differential equations. So, it turns out that second order differential equations are the most commonly encountered type of differential equations in most applications. Some common ones that you have seen are the Schrodinger equation, okay, and the diffusion equation, and so on. But in general, second order differential equations are some of the most commonly encountered differential equations. Okay. So now what are the techniques that we use to solve second order differential equations, and for now we will restrict ourselves to ordinary second order differential equations. Okay. So, okay. Now, second order differential equation is something that contains y double prime. So, second derivative of y square, okay. It contains y double prime and it contains lower derivatives. Okay. So, the lower derivatives will be y prime and x. So, it is an equation containing y double prime, y and x. So, you can write it as some function of y prime y x equal to 0. So, this is a second order differential equations. For example, you can have y double prime plus 2y equal to 0. This is an example of a differential equation. So, it contains, this particular equation contains only y double prime and y, okay, but in general it can contain all those, or you can have x, or you can have okay. So, this contains y double prime, y and x. So, it can contain some or more or all of these, and that is what forms a second order differential equation. Okay. Now, let us look at some types of second order differential equation. A linear order differential equation. So, a linear second order differential equation is one in which each term consists of only one power of y prime or y double prime, okay, or I should not say only one. So, at most one. So, right way to say it is of maximum one power of y double of y prime or y double prime. So, for example, if you look at these equations, if you notice, if you look at this equation, the first term contains y double prime, okay, second term contains y, okay. So, this is a linear second order differential equation. Similarly, you look at this contains y double prime, this contains only one y prime, this contains y, this is also a linear second order differential equation. So, these are all linear. Similarly, this also contains, each term contains only one power of y, okay. So, an example of a, on the other hand, if you had something like y double prime plus y square equal to 0. Now, this contains y to the second power. So, this is not a linear, this is a non-linear ODE. Similarly, you could have a non-linear second order ODE of the form so, this contains this term contains 1 power of y prime and 1 power of y. So, effectively it contains 2 powers of y or its derivatives. So, this is another nonlinear, this is also nonlinear. Okay. So, you can have linear or nonlinear second order differential equation. So, the most general linear second order ODE. Okay. So, now what is the most general form of this linear second order differential equation? And that is you can write it as y double prime plus a of x y prime plus b of x y equal to c of x. Okay. So, this contains second derivative of y, this contains first derivative of y and some function of x, this contains y and some function of x, and this contains a constant. Okay. So, this is the most general linear second order ordinary differential equation. Now, we have already learnt what a homogeneous equation. A homogeneous equation is one in which each term contains y to the same power of y or its derivatives. So, homogeneous equation linear second order ODE. So, homogeneous linear second order differential equation, that is a special class of these where c of x equal to 0. Okay. So, that implies this is homogeneous linear ODE. Okay. So, this is one class of linear second order differential equations, is the homogeneous one. Okay. So, now there is something very interesting that happens with these homogeneous equations, and that is what we will explore in the rest of today's class. What I want to mention right at the beginning is that if you have a second order differential equation, then the general solution it has two undetermined constants. Okay. So, in general, the general solution of a second order differential equation has two undetermined constants. Okay. And so we need two boundary conditions to solve for particular solution. Okay. So, we need two boundary conditions in order to solve for the particular solution. Okay. So, this is a brief summary of second order differential equations, and what we will do now is to look at various cases. We will look at methods to solve them. We will look at how a general solution can be constructed, okay, and so on. So, that will be the topic of the rest of this class, okay, and the next few lectures. Okay. So, now let us look at the homogeneous equations. So, of the form y double prime plus a x y prime plus b of x y equal to 0. Okay. Now, some of you might wonder why I did not put some function of x here, okay, and the answer is that you can take that function of x and you can and you can include it in the Ax. So, suppose I had a C of x here, then I just divide the whole equation by C of x, and I take that factor of C of x into the A of x. Okay. So, so in a sense A of x can be singular. So, it can go to infinity at some points and so on. Okay. So, now the question is A of x and B of x, both of them can be divergent at some point. So, there might be certain values of x for which these functions go to infinity. Okay. So, so now let's go to certain properties of the solutions. Okay. Now, the property of the solutions that we are most interested in is the following. Suppose y1 and y2 are solutions of, I will call this equation 1 of 1. So, suppose y1 and y2 are solutions of 1, then C1 y1 plus C2 y2 is also a solution of 1. Okay. So, where C1 C2 are arbitrary constants. Okay. So, suppose y1 and y2 are solutions of this equation, then clearly any linear combination of these two will also be a solution of this equation. It is fairly easy to prove. You can just substitute this in this equation. So, if I substitute this in this equation, what I will get is C1 y1 double prime plus C2 y2 double prime plus A of x C1 y1 prime plus A of x C2 y2 prime plus B of x C1 y1 plus B of x C2 y2 equal to 0. Okay. And what you can see immediately is that you take the C1 terms, you will get C1 y1 double prime plus A of x y1 prime plus C2 y2 double prime plus A of x y2 prime equal to 0. Okay. So, what I did is I substituted this in this equation, and when I substitute this, then I take the terms containing C1. So, I have first term is C1 y1 double prime, then I have a C1 y1 prime A of x. So, y1 prime A of x C1, and I will get C1 B of x y1. So, B of x y1, and similarly with C2. Now, this is equal to 0 because y1 is a solution of this differential equation. This is equal to 0 because y2 is a solution of this equation, and so this whole thing is equal to 0, and that implies C1 y1 plus C2 y2 is a solution of 1. Okay. So this is a very important property that says that if you have two solutions to the differential equation, any linear combination of them is also a solution to this second order homogeneous differential equation. Okay. Now, the next question is or the next comment is that is the following: if y1 and y2 are linearly independent, okay, they form a basis for all solutions. Okay, so for all solutions, okay, and I should say this with a little bit of caution, okay, because there might be some solutions that might not be expressible in this form. Okay, so the statement is that if y1 and y2 are linearly independent, so y1 is a function of x, y2 is a function of x. So if these two are linearly independent, and when I say that they are linearly independent, that means they are not proportional to each other, okay, are not proportional to each other, then y1 of x, y2 of x form a basis. Basis for all solutions. Okay, so if they are not proportional to each other, they form a basis for all solutions. Of what? Okay, so the point is you have this differential equation. Okay, so if you know two linearly independent solutions, then any solution can be expressed as a linear combination of these solutions. Okay, so that's the idea. So in a sense, if you have a vector space, okay, you say that any vector can be written as a linear combination of the basis vectors. So same way, if you have this set of solutions, any solution can be expressed as a linear combination of these two solutions. Okay, now incidentally, you also notice that that 0, y equal to 0 is a trivial solution of this equation. So y equal to 0 satisfies this equation in a very trivial way. So actually, you can show that the set of solutions forms a vector space. Okay, this satisfies the axioms of a vector space. So you can say this set of all solutions of 1 forms a 2D vector space. Okay. So it forms a 2D vector space because if y1 and y2 are solutions, then any linear combination of them is also a solution. Okay. So this is a very useful property. So the question, so the biggest question is, how do we find the basis? So how one find this basis of solutions? Okay, so just to reiterate, what we want to do is we want to find two linearly independent solutions, two solutions to this differential equation which are not proportional to each other. So now the question is, how do you find these bases, and that is the challenge of say of the second order differential equations. Okay, and we look at various strategies for finding the solution of these differential equations. So let's take a very simple example, okay, and we'll see how this works. We'll take an example where we are familiar with the solutions, and then later on we'll go to more complicated cases. So let's take the example y double prime plus 4y is equal to 0. Okay, so y double prime plus 4y equal to 0, and you will immediately tell me that this equation is of the form of a simple harmonic oscillator. So this is a simple harmonic oscillator. Okay, and the solution is of the form. So this is y double prime plus 2 square y, or y double prime equal to minus 2 square y, okay, implies y equal to y1 equal to sin x, sin 2x, y2 equal to cos 2x. Okay. So y1 is sin 2x, y2 is cos 2x, and these two are linearly independent, and so they form a basis. So the general solution y is equal to C1 sin 2x plus C2 cos 2x. Okay. So, the general solution to this differential equation can be written in this form, okay. And depending on the boundary conditions, you can put the boundary conditions and you can solve for C1 and C2. So, suppose I give the boundary conditions. So, suppose I say boundary conditions y of 0 equal to 1, y prime of 0 equal to 0. So, these are my two boundaries. Suppose I had these two as my boundary conditions, then what you will do is y of 0 is if I substitute, if I put x equal to 0 in this, so I will call this 2. So, put x equal to 0 in 2. So, x equal to 0 implies the sin 2x term will go away. You will have cos 2x is 1, cos 2 into 0, that is 1. So, you will have C2 equal to 1. So, 1 equal to C2. Okay, so, you have determined C2, okay, and if you do that, then you have y equal to C1 sin 2x plus cos 2x. Okay. So, then you put then you take the derivative. So, y prime is equal to, or y prime at 0 is equal to, so if I take the derivative here, I will get 2 C1 cos 2x, and if I put x equal to 0, cos 2x is cos 0, which is 1. So, I have 2 C1. Okay. In this case, derivative is 2 sin 2x, and when x equal to 0, that derivative goes to 0. So, 2 C1 equal to 0 implies C1 equal to 0. Okay. So, we have determined, so C2 is 1, C1 is 0. So, the particular solution is y is equal to cos 2x, implies y equal to cos 2x. So, this is the particular solution with no undetermined constants. Okay. So, what we had is we had a differential equation y double prime plus 4y equal to 0, and the solution was written as y is equal to C1 sin 2x plus C2 cos 2x. That was the general solution, okay. And we said that the basis vectors are sin 2x and cos 2x form a basis. Okay. So, now the next thing is let's try to do it in a slightly different way. Now, instead of saying sin 2x and cos 2x, suppose I had said I could have said y1 is equal to e to the I 2x and y2 is equal to 2x. Okay. So, what I have said is this is also a solution to this differential equation, this is also a solution to this differential equation, okay, and I could have used this as the solution. Okay. So, this also forms a basis. Okay. This also forms a basis, and you can see that so that implies that our original basis is not a unique basis, there can be other bases also, and that should be fairly obvious because you can write e to the I into 2x is equal to cos 2x plus I sin 2x. Okay. And so we wrote y1 as a linear combination of these two bases. Okay. So this implies that you can go from one basis to the other, okay, and so cos 2x, if cos 2x and sin 2x are a basis, also e to the 2ix and e to the minus 2ix also form a basis. Okay. So you should not be surprised if you get very different looking forms of bases, because indeed the bases are not unique. Okay.